As an aerospace and aerodynamic CFD fluid dynamics expert, MR-CFD offers various CFD products in aerospace field. In this CFD training package, we use computational simulations for aerodynamic to review aerospace and turbomachinery applications. We also train the whole simulations process in current package and the role played by computational fluid dynamics or CFD. Here are 10 aerospace and aerodynamic CFD simulations from the CFD shop that engineers can purchase and use as a template for their CFD analysis from various aircraft systems and components as an aerodynamic and aerospace CFD training package. By clicking on the subscribe button, you will be informed about the newest CFD training videos by MR-CFD. Or if you are watching the training video, click on the MR-CFD logo and subscribe. In this project, we are going to simulate a NACA 0012 airfoil in the compressible airflow field. Domain extents displays the Cartesian coordinates extremes of the nodes in the mesh. We should note that these values are not editable, they are purely informational. Also, X, Y, Z minimum shows the minimum values of the Cartesian coordinates in the mesh, and X, Y, and Z maximum shows the maximum values of the coordinates in the mesh. Okay, also let's have a look on view length unit. The view length unit contains a list of common units of length. The domain extents will automatically be set based on your selection. The units include common SI and British units such as centimeters, millimeters, inches, and feet. The units of length in the set unit dialog box will change each time you change your selection in the view length unit in drop-down list. The mesh display dialog box controls the display of zones, surfaces, and partition boundary meshes. The nodes, edges, faces, and partitions in the options section respectively enables the display of nodes, display of mesh edges, and mesh faces, and even display of partition. Options contains the rendering options. To see the effects of your selection, you must click the display button. Pressure far field conditions are used in ANSYS Fluent to model a free stream condition with free stream Mach number and static condition being specified. The pressure far field boundary condition is often called a characteristics boundary condition since it uses characteristics information to determine the flow variables at the boundaries. There are also some limitations for using this type of boundary condition, I mean the pressure far field. When the pressure far field boundary condition is used, this boundary condition is applicable only when the density is calculated using the ideal gas law. I mean, using it for other flows is not permitted. And the other limitation, it is incompatible with the multi-phase models such as VOF, mixture, and Eulerian that are available with the pressure-based solver. And also, it cannot be applied to flows that employ constant densities, the real gas model, and the wet steam model, which are available in the density-based solver. So these are some of the limitations of using the pressure far field boundary condition. But in this case, we are going to use this boundary condition for our far field boundaries. The momentum also displays the momentum boundary conditions. In the wall motion contains options for specifying whether or not the wall is moving. In this case, we choose a stationary wall that specifies that the wall is not moving relative to the adjacent cell zone. And also for shear conditions, that contains options for specifying the shear conditions at the wall. We choose the no slip option that specifies a no slip condition at the wall. No further inputs are required. Now let's investigate the current number for the density-based implicit formulation. Linear stability theory shows that the density-based implicit formulation is unconditionally stable. And because of this stability, we choose the implicit instead of the explicit. So, however, as with the explicit formulation, non-linearities in the governing equation will often limit stability. The default current number for the density-based implicit formulation is about 5. It is often possible to increase the current number to 10, 20, 100, or even higher, depending on the compressibility and complexity of your problem. You may find that a lower current number is required during startup when changes in the solution are highly nonlinear, but it can be increased as the solution progresses. So at the first we identify 0.1 current number, and after that, after some stability and convergence in the simulation process, we can increase this number. And here in the turbulent contour, we can see that the turbulence start to increase at the separation zone in the suction side and near the trailing edge. So both drag and lift forces, including pressure force and viscous force, and the total force shows the sum of these two forces. Also, for the coefficients of lift and drag, we follow the similar rules. Here is a summary of the steps for defining the problem and its solutions, as a review, and even the equations that we have noted in the results section. The project's aim is to investigate the pressure distribution, rotational phenomena, and flow behavior around a rotating dimpled cylindrical wall. The geometry of the present model is three-dimensional and is designed using SolidWorks software. The geometry of the model consists of a rectangular channel with a cylindrical object inside the interior as a rotating object, and a cylindrical space around the rotating cylinder inside the channel is distinguished. Also, dimples or protrusions have been created on the surface of the cylinder, which has a roughness ratio of 0.5, called the ratio of the depth of the dimple cavity to the diameter of the dimple. Also, since the model is symmetrical with respect to the plane perpendicular to the central axis of cylinder, the geometry of the model is halved to reduce computational cost. The figures show a view of the geometry, and also the meshing of the present model has been done using ANSYS meshing software. The mesh type is structured. The velocity inlet boundary condition is defined for the inlet zone, and the velocity specification method is magnitude and direction. Then the x component of the flow direction is -1. And also there is some symmetry boundary condition is this computational domain, because the geometry is cylindrical, and the symmetry boundary condition is used to just simulate the half of the total geometry and computational domain. For setting under-relaxation factors, we should say that the pressure-based solver uses under-relaxation of equations to control the update of computed variables at each iteration. In ANSYS Fluent, the default under-relaxation parameters for all variables are set to values that are near optimal for the largest possible number of cases. These values are suitable for many problems, but for some particularly nonlinear problems, for example, some turbulent flows or high Rayleigh number, natural convection problems, it is prudent to reduce the under-relaxation factors initially. It is good practice to begin calculation using the default under-relaxation factors. If the residuals continue to increase after the first 4 or 5 iterations, you should reduce the under-relaxation factors. Occasionally, you may make changes in the under-relaxation factors and resume your calculation, only to find that the residuals begin to increase. This often results from increasing the under-relaxation factors too much. A cautious approach is to save a data file before making any change to the under-relaxation factors and to give the solution algorithm a few iterations to adjust to the new parameters. Typically, an increase in the under-relaxation factors bring about a slight increase in the residuals, but these increases usually disappear as the solution progresses. If the residuals jumped by a few orders of magnitude, you should consider halting the calculation and returning to the last good data file saved. In the initialization section, we use the standard initialization because there are just one inlet and outlet in the same direction, so the best method for the solution initialization would be the standard method. And also the x velocity is equal to minus 0.45 meter per second. Just click on the initialize button and we are ready to start the calculation. The first step to display a two-dimensional contour is to define a plane that we are going to show the contour on it. And even the turbulence, kinetic energy contour, and every desired other contour. All the vorticities and vortexes are visible in the vector in this plane, that we can see all the vortexes that are made in the dimpled. As the fluid flow moves through the x-axis, the x direction vector and options of force display the drag force and drag coefficient. This table is a summary of the steps for defining the problem and its solution as a review. The present project concerns the simulation of airflow around a NACA 0015 airfoil and MHD effect. The present issue concerns the simulation of airflow around a NACA 0015 airfoil. This airfoil is a symmetrical airfoil that doesn't produce a lift force at zero attack angle. And we investigate the lift coefficient of this airfoil at different attack angles with and without magnetic or MHD force. In this problem, we study the separation and the maximum angle of attack where the separation doesn't occur. By applying the magnetic force or MHD, the separation happens at the larger angle of attack. The RNGK epsilon model is derived using a statistical technique called the renormalization group theory. It is similar in form to the standard K epsilon model, but includes some refinements. For example, the RNG model has an additional term in its epsilon equation that improves the accuracy of rapidly strained flows. Also, the effect of swirl or turbulence is included in the RNG model, enhancing accuracy for swirling flows. The RNG theory provides an analytical formula for turbulent Prandtl number, while the standard K epsilon model use user-specified constant values. And while the standard K epsilon model is a high Reynolds number model, the RNG theory provides an analytically derived differential formula for effective viscosity that accounts for low Reynolds number effect. Effective use of this feature does, however, depend on the appropriate treatment of the near wall region. These features make the RNGK epsilon model more accurate and reliable for a wider class of flows than the standard K epsilon model. The RNG-based K-epsilon turbulence model is derived from the instantaneous Navier-Stokes equation using a mathematical technique called renormalization group, or RNG method. The analytical derivation results in a model with constant different from those in the standard K-epsilon model, and additional terms and functions in the transport equation for K and epsilon. The K-epsilon RNG turbulence model is used to model transient flows in geometries with high curvatures and air conditioning problems. This term plays the MHD role, and it is imported as a user-defined function. The initialization solution method is equal to the standard initialization in this case, and also the x velocity and y velocity are computed from the inlet. Following this way, we can display all the contours, including the pressure contour. Following this way and displaying the velocity vector, we can see the separation point in the trailing edge of the airfoil. We can see all the vortexes here, that this is in the separation point. Also, by following this path, we can check and calculate the drag force and coefficient, and also lift force and coefficient in the bottom and upper wall. This table is a summary of the steps for defining the problem and its solution as a review. The present study simulates airflow within a supersonic convergent divergent nozzle and examines the behavior of airflow separated from the nozzle in the surrounding environment, considering shock wave. The present two-dimensional model is drawn using Design Modeler software. The geometric structure of the model consists of a convergent divergent nozzle and the throat area, as well as a rectangular space containing a nozzle output. It should be noted that in the present model, the ratio of the cross-sectional area of the nozzle to the cross-sectional area of the throat area is assumed to be 1.5. This figure shows a view of the geometry. Also, the meshing of the present model has been done using ANSYS meshing software. The mesh type is structured and the element number is equal to 9,000. The size of the grids in the area adjacent to the nozzle output is smaller. The right figure shows the mesh of the supersonic nozzle. Also, the three coefficient method of the Sutherland law is defined for the viscosity of the air that makes the viscosity dependent and a function of temperature. And also the inlet temperature magnitude is equal to 290 degrees of Kelvin. The temperature contour. Following this path, we can obtain the velocity vectors. This table is a summary of the steps for defining the problem and its solution as a review. The present problem deals with the flow of water vapor as the primary fluid and the secondary fluid within a steam ejector. Also, the meshing was performed by the ANSYS meshing software. The mesh type is unstructured. Due to the sensitivity of the fluid to the cross-sectional area, manual meshing was used at each of the defined edge to increase mesh accuracy at more sensitive points. Face meshing has also been used to uniform the structure of the mesh. The pressure outlet boundary condition has been used for the outlet of the steam ejector. And also the wall is insulated, so the heat flux magnitude in the thermal condition is equal to 0. And finally, the last contour dedicated to the turbulent kinetic energy. This table is a summary of the steps for defining the problem and its solution as a review. The present study deals with the airflow on the HAWT blades, so that the purpose of the problem is to study the distribution of velocity and pressure on the surface of the blades.
In General Setup tab, you will see different dialog box from scale to units. By clicking on Scale dialog box, a new window will appear. In this window, you may be able to choose different units for different quantities. For example, you can choose different units for acceleration, for angle, angular velocity, and so on. But you left these quantities without changes. Just click on the Close button. By clicking on the Inlet boundary condition, you will see that the type of this boundary is defined as velocity inlet. By clicking on the Edit button, we will be able to change the settings for this boundary. After clicking on the Initialization button, a new window will appear, and you can choose between two methods of initialization: hybrid initialization and standard. In the standard method, you will be able to choose and set the value for different parameters of the flow field based on your idea, or actually you can choose from the Compute From drop-down list. These values refers to the values used in the first iteration of the simulation process. You can go ahead and choose the all zones so that the software will automatically calculate the values averaging from all the zones. In this velocity contour, you may see the velocity distribution in the middle plane of the rotor domain. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
Combustion chamber CFD simulation.
In General Setup tab, you will see different dialog box from Scale to Units. By clicking on Scale dialog box, a new window will appear. After double-clicking on the method, you will see that a new window will appear showing you the pressure-velocity coupling, which in this project is set to be coupled. Also, you can see that the spatial discretization methods are shown in this window. For example, the pressure discretization is defined to be second order, or for the momentum, second order upwind. Also, you can change this discretization into other formats, like you can change them into first order upwind. As can be seen in this contour, the temperature in the middle of the chamber is increased, showing that the combustion process is taking place. Also, you can see that at the outlet boundary condition, the exhaust mixture also has an increased temperature. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
The problem is going to simulate the supersonic airflow encountered by a two-way oblique airfoil barrier passing through a channel, thus investigating fluid behavior and creating a shock wave phenomenon.
In General Setup tab, you will see different dialog box from Scale to Units. By clicking on Scale dialog box, a new window will appear. In the Open dialog box, we are able to change the settings of our material. For example, in this dialog box, which is related to the air, we can see that the density and the CP, specific heat, thermal conductivity, viscosity are shown. Since we are simulating the compressible flow in this project, you need to go ahead and change the density from the constant to ideal gas. After clicking on Edit for this wall type boundary condition, then a new window will pop up, enabling us to change settings for this boundary condition. Like previous steps, after clicking on Thermal tab, you will see that the thermal condition defined for this boundary is set to be heat flux, and the value for heat flux is defined as 0, which means that this boundary is also adiabatic. As was mentioned earlier in the introduction part, shock wave occurs when a body is moving faster than the speed of the sound in a fluid. Now in a subsonic flow, the propagating pressure waves have enough time to inform the upstream flow to change their direction in order to path around the object. However, in a supersonic flow, the object is moving faster than these pressure waves and not letting the fluid to change its direction. A shock wave occurs when the Mach number, which is over 1, drops below 1 in a sudden move. As can be seen in this contour, the speed of the flow is over 1 Mach. After the flow hits the object, the flow's Mach number suddenly decreases and drops below 1, which causes the normal shock to happen. As you can see in this picture, the shock wave envelopes have formed. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide alongside the ideal gas equation, which is our main equation, and we have based our premises and assumption on this equation.
The problem is going to simulate the airflow inside an axial flow compressor rotor NASA 37.
In General Setup tab, you will see different dialog box from scale to units. By clicking on Scale dialog box, a new window will appear. You even are able to see the mesh for different parts of the geometry. You can do this just by clicking on the Edge option on the left of this appear window and then clicking on the display button. And as for the thermal condition of the valve, you may see that the heat flux thermal condition is defined, and also the heat flux rate is set to be 0 for this valve. After double clicking on the residual button, you will see that a new window will appear, showing you the absolute criteria for the residuals of each equation. For example, you can see the absolute criteria for continuity, x velocity, y velocity, and so on. This criteria refers to the difference between the errors of each iteration, and it refers to the fact that if the error is less than these criteria, those equations have reached convergence. Also, as you can see, the convergence criterion is set to be in absolute form. As can be seen in the velocity contour, by getting away from the center of rotation, as was expected, the speed of the blades will increase. And by increasing in this speed, the airflow velocity will increase as well. Finally, in the velocity vector contours, you can see the vectors of velocity and the direction the airflow moves. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide alongside the ideal gas equation, which is our main equation, and we have based our premises and assumption on this equation.
The present problem simulates the cooling of a turbine blades. Also, from the mesh display section, we can see all the boundaries and their surfaces. The flow regime is assumed to be a laminar flow. If we consider the buoyancy effect in the simulation, the velocity will not be equal to 0 anymore. By the way, this is the way to make a desired plane in every direction, in every dimension that we want. So following this path, we can make every desired plane. To show, of course, the contour on that. Here is the summaries of the problem definition and problem solving steps in the table as a review. Obtain the mesh file and also the full training movie by purchasing this product. By clicking on the subscribe button, you will be informed about the newest CFD training videos by MR-CFD. Or if you are watching the training video, click on the MR-CFD logo and subscribe. To benefit from MR-CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.